You're live, Daniel.
Okay, I was waiting for something to tell me about it.
We are very happy to have Daniel Mayerson from Saclay,
no.
who'll be kicking off the conference with the first talk. So, welcome.
Okay, thanks, Joseph. No, I was waiting for like a thing saying this meeting is being recorded or something like that.
No.
But that's all right. Okay, good. So, good. Yeah, thanks for letting me kick off the new Black Hole Microstate conference. So I'd like to tell you a little bit about some work that that I've been doing together with a bunch of people who I list here and also here, and who other people have been doing as well, all sort of on the topic of how to spot microstructure in the wild, right? So here is my attempt at a joke here, where, you know, the fuzzy things here, you should think of them as fuzzballs, right? And, you know, the idea is, you know, how are we going to actually be able to go out and see these guys in real life observations, right? That's sort of the idea. And so I'll be talking a bit about this topic in general, which is going to be based somewhat on a review that I wrote last year. I'm also going to be talking some length on some new work on Fuzzball Shadows, which was with these authors, that I think is I think it's very exciting. So I'd like to share that with you guys. Okay, so just to give you a little outline of what I'm going to be talking about, or what I hope to talk about. First, I'm going to set the scene, right? So I want to tell you why should we be interested in this? Why do we study this kind of thing? And what is it exactly also that we're going to be studying, right? So I just want to set the scene and give you sort of the big picture philosophy as to what's going on. Once I've said that, then I can move on to also setting the scene for, you know, because a lot of us here are theorists, and so we might not be very familiar with the actual observations or experiments that we want to make contact with when we do these kind of studies. So I'm going to talk about those briefly. And then I'll talk about a few topics, depending on time, probably only touch on 2 or 3 of these before moving on to Fuzzball Shadows, which I want to talk about for approximately a half hour. Okay. So obviously feel free to interrupt at any time, ask questions or tell me that I'm wrong or you know, whatever. I welcome the interruption, right? So I'm going to go over a few things relatively quickly because I assume that most people in the audience will be familiar with them. For example, when I talk about, you know, the information paradox, this will be very quick. But so if you want more discussion on that, just let me know. Okay, so you know, this is my 1-slide philosophy summary, let's say. GR, right? We all know that as soon as GR was given to us by the heavens, we were also given black hole solutions by Schwarzschild first and then by other people later. These black hole solutions already predict their own demise, right? Because we know they have singularities. And when you think about them a little bit more, you have things like the information paradox. In any case, what you expect in quantum gravity is that something happens with this black hole, right? It's not just going to be the general relativity black hole. Now, if you believe in small corrections, large corrections, whatever you believe the case to be, you sort of expect something that the black hole is not really exactly the general relativity black hole. Okay, now when you think of this from a phenomenology point of view, right, when you do have observations involving black holes, then this means that you might be able to distinguish the general relativistic prediction of what you're seeing, right? The general relativistic black hole and a quantum gravity object, whatever it may be. Okay, and now typically what people do to model this, to understand this in phenomenology, or to understand what the observable consequences might be, is one introduces something that's called an exotic compact object, or an echo. And so this exotic compact object has to be something where you've replaced the black hole of a given mass by something else, which is a little bit larger than the black hole might be, right? So if RH is the horizon scale of the black hole of this given mass, then this compact object, you know, because it doesn't have a horizon, has to extend a little bit beyond the horizon scale. It can't be a lot beyond the horizon scale because then it wouldn't really be something that mimics a black hole very well. It has to be sort of around, but a little bit larger than the horizon scale. So you sort of parameterize this by saying that the object is parameterized by a scale R0, which is a little bit larger than the corresponding black hole radius might be. And so this epsilon needs to be much smaller than 1. right? So that's why it's a compact object. Why is it exotic? Well, if you think of classical GR, you have something called Buchdahl's theorem, which tells you that if you have any kind of normal classical matter, then this thing needs to extend to epsilon larger or equal to 1/8, which is already pretty big, unless you if you don't, then it'll collapse into a black hole, right? If you make it any more compact, it'll collapse. And so what you need to have, you need to have some kind of exotic matter, exotic mechanism to keep this epsilon very small without it collapsing into a black hole. Okay, the actual echoes that are used typically in phenomenology are bottom-up models, right? Are sort of, you do what you can, right? And so in particular, there are things that are called boson stars, where you add to the Einstein-Hilbert action, you just add some kind of scalar field, and that gives rise to some compact objects, which are basically configurations of the scalar field. You can also make wormholes. These are not the string theory or holographic wormhole. These are more like just, you have the Schwarzschild metric, for example, and you go in by hand and change some of the metric components, right? And so because you're changing these metric components by hand, you're also introducing some kind of exotic matter, which you don't really have a motivation or an origin of. You just sort of say, well, if I have a wormhole, then it must be supported by this matter, right? And so there's lots of other models too, like gravastars, et cetera. But all of these sort of have in common that, they come from a bottom-up approach, right? So they lack some kind of a top-down quantum gravity motivation, right? It's more of an effective field theory kind of idea. And I think this is where fuzzballs really shine and come in, right? Because fuzzballs are really quantum gravity motivated objects, right? I'll introduce fuzzballs in a second if there's people here that don't know exactly what they are. What they are quantum gravity top-down objects that replace a black hole, right? So they are really exactly within this class of objects that are a little bit bigger than a black hole of the given mass, but don't have a horizon anymore, right? They have a horizon scale microstructure. That's something that's a phrase that's used a lot. And so I think a very obvious question to ask is, if you replace your black hole by this fuzzball echo, right, this fuzzball compact object, what kind of signals might we be able to see in observations, right? That's sort of the idea. And putting this in contrast, right, with the bottom-up models that are typically studied, which have a lot of pitfalls, right, like not being able to understand where the exotic matter comes from or whatever. Okay. So fuzzballs, right? Let me introduce the idea of fuzzballs. I think most, if not everybody here, is going to be very familiar with fuzzballs, so I'll be relatively quick, but nevertheless, I think it's good to sort of set the scene a little bit. I like to do this using the information paradox, right? So, okay, the information paradox is quite simply explained as there's a bunch of information that's trapped inside of a black hole, right? Because stuff has fallen in or collapsed and formed the black hole. No information can come out with Hawking radiation, right? That's the only thing that comes out of a black hole, but it's thermal, so it carries no information. And so the question is, what happens with the information that's trapped inside the black hole? It seems like it can never come out. And now you might say, well, okay, Hawking radiation, this is some kind of a semi-classical calculation. Really, what I need to take into account is small corrections to this semi-classical calculation. And maybe, these small corrections might give you the actual information that comes out, right? But then I think a very important theorem by Mathur is that under certain assumptions, right, such small corrections at the horizon scale, small corrections to Hawking radiation, this is not going to be enough to retrieve the information out of a black hole. Okay, this is not going to be able to do it for you. And so you're sort of left with this paradox that you need to resolve. And I think there's roughly 3 ways to do this, right? One way is to say, okay, the Hawking radiation is thermal or approximately thermal, and when the black hole is radiated away, you're left with this small Planck size remnant. And the small Planck size remnant carries somehow all of the information that the black hole had before, right? This is, I think, a logical possibility. However, it's maybe a little bit unsatisfactory because then you're left with a remnants that have to be arbitrarily small and carry arbitrarily large amount of information. A second way out is to allow for non-local effects, right? And I think that both the Papadopoulos-Raju proposal and Gidding's nonviolent non-locality proposal, these fit into this kind of a category, right? Also the islands proposal, which I certainly don't want to talk about here, but will be talked about a lot in this conference. This, I think, also falls under this general NOMA, right? But the fuzzball paradigm really falls under this third category, which is that, you know, small corrections at the horizon are not enough. Therefore, what we really need is large corrections at the horizon, right? So whereas you might think that a black hole, right, has a large curvature only near the singularity, so way deep inside the black hole, and so quantum corrections will only be important down there, what the fuzzball paradigm is telling you is no, what you really need is you need quantum corrections, stringy corrections, microstructure that extends all the way to the horizon scale, right? That's really what's going on. So if you want to sort of make this in a picture, right, you have the black hole, right? If this is the horizon and then this is the singularity, you're not just fuzzing out the singularity here. No, you're really saying that you have some quantum stringy fuzzy object that extends all the way to the horizon scale, right? It's this very big object. Okay, that's sort of the nutshell of the fuzzball paradigm, and these fuzzy objects that replace the black hole are the fuzzballs. Right? Okay, so let me make a further distinction here between a generic kind of fuzzball, which is anything that fits under the NOMA that I was just describing, and something that's a microstate geometry, right? So in general, what you expect is that a black hole, since it has a horizon, has an entropy, it can be seen as some kind of an ensemble of microstates, right? Because it has an entropy. It can be seen as some kind of a thermal average or ensemble of microstates. Each one of these microstates is a fuzzball, right? So fuzzballs are basically the individual microstates of the black hole. So because they are microstates of a black hole, they have to look like a black hole from far away, right? If you're very far away from the horizon scale, then you can basically not distinguish between a black hole and a fuzzball, roughly speaking, right? They have the same charges, mass, whatever. However, the big difference, of course, is that the fuzzball does not have a horizon, right? It's horizonless. And so this is true for fuzzballs, and this is also true for microstate geometries, right? But now what I want to do is I want to distinguish fuzzballs and microstate geometries. Whereas a generic general fuzzball is something that you might expect to be, this lives in quantum gravity, so it should be a very quantum stringy object. Very special fuzzballs, very specific fuzzballs can be constructed, can be considered that are coherent states. So these are sort of the things that approach the most classical state. And so because they're coherent states, they can be approximated by or described by a semi-classical geometry, right? A geometry meaning a metric and a solution within an actual gravity theory, within a supergravity theory. Okay, and these should also be smooth solutions within the supergravity theory because they correspond to, there's no horizon, and there should also not be any singularities in it, because in string theory, in the full string theory, they should not have any problems, right? They should be well-behaved quantum gravity objects, right? And this is in contrast with generic fuzzballs, which are quantum stringy objects, which we can't really study directly. We can only sort of use generic hand-waving arguments to say, well, this or this or this should be generically true. Whereas with microstate geometries, you have explicit solutions that we can write down and explicitly go into the supergravity theory and study them, right? And so these are also going to be the guys really that we're going to be interested in studying when we're talking about observations, right? Because these are the guys that we have available to us. Okay, now some limitations of these microstate geometries that might already be apparent from what I've been saying is that well, one thing that I haven't said yet is that, you know, a lot of the microstate geometries that we know that we have constructed are supersymmetric, right? A lot of them are also not asymptotically flat or live in higher dimensions, but let me not focus on that. It's hard. This is sort of more of a technical thing, right? It's just hard to construct these microstate geometries, and it's much harder to construct them if they're not supersymmetric. Nevertheless, some exist, and I will talk a little bit about some of these in a bit. But I think it's fair to say that there are no microstate geometries available for realistic black holes, right? So if you ask me, well, okay, I'm interested in this Kerr black hole that's sitting in the center of the galaxy, and I want to know, well, what kind of microstate geometry corresponds to this Kerr black hole, then I don't have an answer for you, right? There's no microstate geometries for those. Moreover, we don't know the answer to a lot of dynamical questions, right? We don't really know how they form explicitly. We don't know how they evolve. We have some studies, some indications as to what should or should not happen. But in general, this is a very hard question, of course, to ask how these things, what the dynamics of these things are. This is also related, of course, to the fact that supersymmetric microstate geometries, because they're supersymmetric, don't really have a lot of dynamics going on, right? And then finally, like I was saying, microstate geometries are these coherent semi-classical states. So they're not a generic state, right? They're a very, very special kind of state. And so an objection that you might have is that they could be very different from what is a typical fuzzball, right? Because a typical fuzzball is going to be some generic quantum stringy superposition of all kinds of states, and so might have very little to do with our semi-classical approximation or semi-classical states that we can actually study, right? And so I think all of this is sort of pointing towards the philosophy that I'd like to use, which is that we shouldn't really be taking these microstate geometries too seriously, right? We shouldn't be saying, well, let me take this supersymmetric microstate geometry and compare it to an actual observation and see if it matches my actual observation, right? That'll probably be too far. It might be a good exercise to do this, but we should be mindful that we really would be wanting some realistic microstate geometry, right? Instead of a supersymmetric one, for example. Okay, so the thing that I want to say is that we should think of this as using toy models, right? The geometries that we have, we can study them and identify some universal properties in these observations or observables in these geometries, which can qualitatively point towards observables that we want to focus on in actual experiments, right? So we might identify some generic feature that all microstate geometries have that one might be able to just go out and measure in an actual observation that might be a smoking gun to some microstructure, right? It won't be a smoking gun to a particular microstate, but we want to identify what might be a smoking gun for any microstructure at all, right? Compared to a black hole. Okay, so I'll be more concrete in a few examples later on, but for now, let me just say that this is one example of a generic feature is simply the mechanism or the reason of being, right? The way that these things can exist, these microstate geometries, right? So what a microstate geometry or a general fuzzball is expected to be is to have the same kind of structure as a black hole as you approach the horizon, right? You have some kind of a redshift throat. So as you approach the horizon structure, you have the same kind of redshifting that you would have in a black hole. But then when you think you're approaching the horizon, instead the spacetime ends in this smooth kind of microstructure cap, right? But then your question should be, how is this cap prevented from collapsing on itself, right? How is this not just collapsing into a black hole? And so the generic feature that all microstate geometries have, and so you can sort of expect this to be a typical feature, is that they're prevented from collapse by the non-trivial topology, right? And it was sort of shown that this is the only way that you can have solitons, right? That you can have mass, non-trivial objects of horizon scale size without collapsing into an actual black hole. And so this generic feature, I'm not saying this is an observable or something that we can go out and measure directly, but this is already one example of a generic feature that microstate geometries, special semi-classical microstate geometries, have taught us about the generic structure of fuzzballs, right? So something like this, but for observations, is what we're sort of moving towards. Okay, so let me just try to reiterate or summarize this philosophy, right? This fuzzball phenomenology, right, is the idea that we should really think of fuzzballs as these compact objects, which we can use in observational phenomenological studies, that as opposed to the other echoes that people study, these guys are top-down and quantum gravity motivated. Right? And so this is, I think, one of the key points about fuzzballs that make them so interesting to study. We can study them explicitly, or the ones that we can explicitly study are going to be microstate geometries, these special solutions. And we want to be looking for robust features, universal properties. And so I mentioned topology as a mechanism for having solitons without horizons, right? So we want to be identifying these universal properties in these models that might give rise to looking for smoking guns of string theory microstructure, right? This philosophy is not new in the sense that this has been done before. For example, in ADS-CFT, when people were looking at holographic QCD, actually, this is still a field that exists, of course, and also in condensed matter, holographic condensed matter, what people do is not try to say, well, I think I have the holographic dual to QCD. That's a very hard question, but rather one studies some kind of a superconformal field theory, which is dual to something, to some gravity theory, where we can make some statements. Since this field theory is strongly coupled, we can make statements that we expect or hope to be universal for all strongly coupled field theories, including QCD, right? And I think the most famous example of this was the viscosity over entropy ratio, which in holography was shown to be 1/4 pi, which is true for any strongly coupled field theory dual to an Einstein gravity. And so this was, in a sense, this is the prototype universal property or universal results that you get out of holographic calculations. And this was also so this is a very small number compared to what you expect for other materials, other matter. And this was very, very near the experimental value that was found for actual QCD experiments in various accelerators. And this was also sort of the only quote unquote explanation or calculation that led to a number of this order of magnitude. Right, so this was sort of a very, very famous result a number of years ago. Okay, so this is the kind of idea that we should have, right? We want to identify some universal properties of microstate geometries, of observables of microstate geometries that are going to point us towards what will be the smoking gun observable or observation that we should work towards, right? And so this, you can also see this as a two-step process, right? We really do a direct phenomenological study of the geometries we have, right? So we ask ourselves, what happens if this is the geometry that we're observing in some experiment? And then we try to extract the universal features of these kind of experiments, these kind of observations. And then we can go a step further and try to model this in a more generic fashion, not studying one or two geometries, but model in a generic fashion what the string theory effects would be, the string theory microstructure effects will be in observations. So I'll give you a few examples of this along the way, right? And so I just want to emphasize this is a new field where there's various people have done some work on this, but there's so many other things to do, right? So feel free to jump in. Okay, so this is where my introduction ends. Just pause here for questions if there are any. Questions or comments? No? Okay, so I'll move on to. No? Okay. In that case, I'll move on to the actual observations. So this is again to sort of set the scene for the framework, or let's say the things that we should have in mind, right? When we talk about phenomenological studies, we should have some kind of an observation or experiment in mind. So there's two of them. The first one of which is gravitational wave experiments, right? The new window to the universe that has opened to us since 2017. And typically what we're interested in is what we see is the in-spiral and merger of two black holes, right? So you might also be interested in neutron star mergers, but let me focus just on black holes. This picture is the waveform, right? This is the actual gravitational wave that we detect, if you will. And so what you can clearly distinguish is three phases, right? You have the first phase, which is the in-spiral phase, where the two black holes are still quite far away from each other, spiraling around. and slowly losing energy, right, due to gravitational radiation. Right? This orbit slowly loses energy. And so this is the in-spiral phase where the gravitational wave is of relatively low amplitude. Then as the two black holes get closer and closer, at some point they're going to enter the merger phase, which is really the phase where the two black holes start really overlapping, the horizons start to coalesce. It starts to be, two objects become one, right? And this is the regime where you can see the strongest signal. This is also very short phase. And as opposed to in the in-spiral phase, which is sort of accessible to perturbative GR techniques, if you want a handle on the real physics in the merger phase, right? This is in the strong field regime. You really need to be using numerical GR to describe this correctly. And then finally, once you've sort of coalesced into one object, this final object is going to quickly relax into its final stationary state. And this relaxing is called the ring down phase, right? So, and this can be described very accurately by taking a single black hole and describing perturbations on top of it, right? That's because you've sort of formed the final black hole. And so in each of these phases, you can talk about different observations or observables that are important, properties of black holes that become important there. So I'm not going to talk at all about the ring down phase, although there's a lot to be said there, but I just want to point you to the talk of Paolopani in the afternoon. Things that are important there are going to be quasi-normal modes and echoes, all related to the ring down of these perturbations of the final object. Instead, I'm going to focus a little bit on multipoles and tidal effects, right? So again, I'll introduce these in a bit, but the multipoles and tidal effects are things that you should be thinking of situating here, right? This is going to affect the way that the two black holes or two objects spiral around each other when they're still relatively far away. And so it might affect this part of the gravitational wave. The second observation that you might have in mind is the EHT, which is also something very new. This, of course, is in the electromagnetic spectrum. And so what the idea here is you're really taking a picture of a black hole. Now, okay, if you're taking a picture of a black hole, you need something to provide you the photons. And what is doing this is, what is giving you the photons is the plasma, the accretion disk around the black hole, right? So every black hole, or many black holes, have accretion disks, which are this highly excited plasma around it. And this plasma emits photons, and then these photons get lensed by the black hole and end up in our telescopes. And so we end up with a picture like this once it reaches our telescopes. Okay, now, so how do you understand these pictures? How do you model these pictures? Well, what you typically do is you need to consider magnetohydrodynamics of the plasma in a GR background, right, in the black hole background. So this is the resulting image that you would get if you do a perfect GRMHD simulation, and then you understand where all the photons are coming from the plasma. And then, of course, because the actual observation of the EHT is blurred because we don't have a perfect resolution, you pass this through a blurring filter and you end up with a simulated image that looks like this, right? So this is roughly how you compare your simulation to data. The thing that I want to emphasize about EHT images or black hole imaging in general is that the main uncertainty in the image is not due to the gravity or small detailed gravity effects, right? And so the main uncertainty is really due to the plasma, right? There's a lot of uncertainty in the plasma physics, in particular in these GRMHD simulations. There are a lot of parameters that describe the physics of the plasma, the physics of the electrons in the plasma, that we don't know how to fix, right? They're not fixed by any a priori science. And so these are sort of tunable parameters. And for a large range of these parameters, you can actually reproduce images that mimic very well the actual image. Right? So there's a lot of uncertainty in the actual physics of the accretion disk. Because there's such an uncertainty in the physics of the accretion disk, it's very unclear whether just looking at this image or images like this is going to be enough to distinguish the detailed, to make detailed gravitational observations, right? So the effects of microstructure, replacing the black hole by something that looks very much like the black hole, but differs in some subtle ways, it's not very obvious if we're going to be able to actually see this in images. Okay, now I will return to this at the end of my talk when I'm talking about shadows and images, and give you an idea of how you might get around this this problem. Okay, so any questions on observations before I move over to the yes, right. So as I said, I'm going to be talking about shadows and basically about geodesics, right? How null geodesics, how photons behave around around the black hole is how the shadow is formed, how the image is formed. So I'm going to be talking about that later. Okay, so any questions on observations before I move to my first actual observable topic? Okay. All right, so let me move on to, oh, yes, please.
I can ask a basic question. So in this middle picture, is this the image of the black hole in some sense from the top, or are we seeing it sideways?
Oh, yeah, good question. I'm not exactly sure what the inclination is for this guy. But roughly speaking, it doesn't really matter that much. You will always see this kind of a ring structure,
because even if okay, you can even see the other side of the accretion disk because of the gravity.
Yes, that's right. Yeah.
Okay.
Yeah, something like that. Yeah.
So it can be from the top or sideways.
Right.
Okay.
Right. Yeah. So I think in particular, the inclination here is probably going to be the inclination that we think the actual M87 black hole is at, which is something's telling me this is like 17 degrees. I'm not sure if this is something I remember correctly or not. But in any case, 17.
70 means is it near the top or near the side?
Near the top, right? Well,
okay.
If you define top.
Okay, so it's like 20-degree polar angle.
So if this is, so I think if this is the z-axis, then it's like the black hole is like this is 20 degrees.
That's
right. If this is a z-axis like that,
okay,
then the black hole is tilted towards us like with 17 degrees.
Okay. Thank you.
Yeah. Yeah, but these ring structures are this ring structure here. This is something that I'll come back to because it'll be important. This ring structure that you see here is a very robust feature and doesn't depend so much on the inclination. Although the intensity sort of does, right? So the intensity that you see here on the bottom, there's more intensity that sort of depends on the inclination of it. Okay. Any other questions? Okay, great. So thanks for the question. So so I'm going to be focusing on multipoles. Now remember, multipoles is something that will appear here in this in-spiral phase, right? This will be important for the in-spiral phase. This will alter how the black holes are going to be orbiting around each other. So what are multipoles, right? Let me start with that. Now in electrodynamics, this is something that we're pretty familiar with, even if we've never given it this particular name. We can always expand the electrostatic potential in powers of 1 over r, and then each successive power of 1 over r gives us some information about the charges in the system, right? So the 1 over r term gives us the total charge in the system, or the monopole charge. The 1 over r squared term is going to give us dipole, quadrupole, and then we get quadrupole and octupole, et cetera, et cetera. So this tells us something about how what the configuration of charges is. Now you might be worried about GR, about doing the same in GR, because in GR we have coordinate transformations, general coordinate invariance, and so it's not obvious that we can actually do such a 1 over r expansion, which gives rise to coordinate invariant multipoles, right? And this is a correct worry to have, of course. However, Garrick and Hansen and Thorne described in the 60s and 70s how to get around this, how to carefully define things that are coordinate invariant multipoles. Okay, and so roughly speaking, right, you have to be a little bit more careful than just doing this in any old metric. But roughly speaking, if you have an axisymmetric metric, then there are two families of multipole moments. The first family is related to the 1/r expansion of the GTT component, and these are called mass multipoles. The 0th of which is simply the mass, of course, of the system. This is very familiar to us. And the second family is called the current multipoles, which are related to the 1/r expansion of GT phi, right? And so S1 is simply the angular momentum, which is also something familiar to us. So the lowest multipole moments are the familiar mass and angular momentum, but all of the higher multipole moments, just like in electrostatics, electrodynamics, tell us more about the intricate features of the geometry. And so in particular, the most basic example, of course, is Kerr, which is parameterized by two parameters, M and A. And of course, because of black hole uniqueness, there can be no other parameters present that the multipoles depend on. And so indeed, the multipoles are completely determined by these two parameters. In particular, the even mass multipoles, right? So these guys are simply M times some power of A. And the odd current multipoles are also just M times some power of A. And curiously or interestingly, the odd mass multipoles and even current multipoles, right? So these guys are all vanishing for Kerr. Right, so in a sense, this is the simplest or basic example to which you should always have in mind when we're talking about multipoles of some exotic object. Because if you want to compare it to some astrophysical Kerr black hole, then this is what you need to be comparing to, right? These values. And so in particular, let me talk a little bit about how you might achieve such deviations in string theory, right? So first, let me say to set the scene, what do we expect to be able to actually measure in experiments? And so in LIGO Virgo, this is less obvious that we will be able to detect differences in these higher multipole moments. But in LISA, which is going to be the space-based telescope launching in the 30s, we expect to be able to measure the quadrupole, which is the M2, just sort of the lowest non-trivial multipole after the mass and angular momentum. We expect to be able to measure deviations from the Kerr quadrupole within 1 part to 10 to the minus 4. Right, so this is pretty impressive. However, it should be said that this is an estimate for how well we can measure the quadrupole moment. It's a lot less clear that we can actually measure higher multipoles to any kind of meaningful precision, right? It's depending on how high you want to go. So the lesson here is quadrupole. We're pretty confident that in the near future horizon with LISA, we'll be able to have a pretty stringent constraint on them. But for higher multipoles, this is not obvious. Okay, now remembering the multipoles of Kerr, there's a few things that I want to say about string theory geometry, string theory inspired multipoles, let's say. Right, the first thing is that when we have microstate geometries, we kind of this is not an obvious statement, or okay, depending on who you talk to, this is an obvious statement or not, but it is true. You can rigorously show that the multipoles of a microstate geometry are going to be approximately those of the corresponding black hole, right? Because every microstate geometry corresponds to some black hole, plus some small deviation around this black hole, right? And so when we're talking about, so let me be very, very precise here, right? The black hole that I'm talking about here is going to be some string theory black hole. Is going to be some string theory black hole that is not necessarily a Kerr black hole, right? Because remember, we don't have any microstate geometries of Kerr. So when we want to compare the multipoles of microstate geometries to the multipoles of Kerr, I like to see this as a two-step process, right? You can compare the multipoles of the microstate geometries that we have to the multipoles of its corresponding black hole, right? That's sort of step one. So this is step one. And then you compare the black hole. I shouldn't write it at the deviation. You compare the multipoles of the black hole with the multipoles of Kerr, right? So this is sort of step two. Okay, and so what I'm saying now is that multipoles of the microstate geometries are always going to be approximately, within some random deviations, the multipoles of their corresponding string theory black hole. And so when I now want to compare the multipoles of the microstate geometries to the multipoles of Kerr, right, the actual observable consequences of multipoles, then I'm actually going to focus more on the multipoles of the actual string theory black holes themselves. And this will actually tell us some interesting information already. Okay, so now in particular, what I'd like to do is I'd like to focus on a class of geometries, which includes black holes and microstate geometries, which are called almost BPS. Now, these almost BPS geometries, without going into any details, are very attractive from a phenomenological point of view. Okay, so not only are there microstate geometries available for these black holes, but these black holes, right, have some properties which are very interesting phenomenologically speaking. You can have a non-zero rotation, which sets them apart from four-dimensional supersymmetric black holes, which always have to be static. So this is already very interesting, right? Because we can have rotating black holes, and Kerr black holes rotate. So this makes it interesting to compare to. They're not supersymmetric anymore, as I said. And as we showed in our recent paper, you can even construct such almost BPS black holes that have a small charge, in a sense, right? So whereas let's say the standard lore or standard intuition is that any kind of supersymmetric extremo black hole always has to have roughly m equals to q, right? Mass equals to charge, and so the charge is always of order the mass. We show that it's actually possible to construct such almost BPS black holes in 4 dimensions where the charge is very, very small compared to the mass, which makes it even more phenomenologically interesting. Now, from a point of view of multipoles, you can even engineer an almost BPS black hole that has the same mass and angular momentum, of course, but also the same quadrupole as a Kerr black hole. Right? So this particular almost BPS black hole will only differ in the even finer structure, right? The even higher order multipoles when you compare it to Kerr. And so in that sense, these almost BPS black holes become very, very interesting objects to replace a Kerr black hole by, because I'm able to, have up to the quadrupole match with the Kerr black hole that I thought was up there. Okay, so this is all sort of to tell you, these first 3 parts are sort of to tell you that almost BPS black holes are very, very realistic, quote unquote, geometries in this very specific sense, and so we can really take them seriously as phenomenological objects. This last point here is where I would like to emphasize where the smoking gun might lie, right? For if we want to distinguish almost BPS black holes from Kerr black holes, but also actually, this is generic, any string theory black hole in general satisfies this too, namely that the odd parity multipoles are turned on, right? So the odd parity multipoles are not vanishing. Now, what are the odd parity multipoles? It's exactly these guys here that are vanishing for Kerr, right? So the odd mass multipoles and even current multipoles, those are all the odd parity multipoles. And so as soon as one of them is turned on, what you break is a symmetry of Kerr called equatorial symmetry, right? Now, just in case this is not familiar to, right? If this is your Kerr black hole, so it's rotating around this z-axis, and this is your equatorial plane here in the dotted line, then Kerr satisfies a flipping symmetry where you send z to minus z, right? So the top half and the bottom half are equivalent. They're you can mirror. They're mirror images of each other, and it's sort of important to. So this is called equatorial symmetry, and it's sort of important to realize that this symmetry is, in a sense, accidental, right? There's no theorem that tells you that stationarity or axisymmetry leads to equatorial symmetry, right? There are theorems that tell you that axisymmetry and stationarity are very well acquainted, right? And that one comes with the other. But there's no such thing that tells you that equatorial symmetry is necessary in any sense. And indeed, in general, string theory black holes, and in particular almost BPS black holes, break this equatorial symmetry, right? And so these multipoles that break the equatorial symmetry are turned on. And this is a very generic feature of microstate geometries, but also of just general string theory black holes, including these almost BPS black holes, right? And so this is sort of the first example where, let's review the steps here, right? We've looked at some explicit microstate geometries in string theory, right? In particular, the almost BPS black holes and their microstate geometries. We've identified something that seems to be very universal, namely the breaking of equatorial symmetry, or the non-zero odd parity multipoles. This is a universal feature which we might now say, well, this might be something that we need to be taking seriously in terms of modeling actual observations, right? Because if you find that odd parity multipoles, if you go out and measure them, right? If you go out and measure some black hole and you measure its odd parity multipoles, you measure if it satisfies equatorial symmetry or not. If you find that equatorial symmetry is broken, this is sort of a smoking gun for some kind of deviation to occur, right? This is sort of where I'd like to put the emphasis, right? These odd parity multipoles, I think, is a very exciting opportunity. And as far as I'm aware, in a lot of phenomenological studies, people have maybe identified that these exist, these odd parity multipoles, but nobody has really done a systematic study of, okay, let's understand how detectable the effects of these things are. So I think that's a very interesting thing to pursue. Okay, so I'd like to move on to tidal effects now. Is there any questions on multipoles?
May I ask a question?
Yes, please.
Okay. First of all, these almost BPS geometries, do they have an ergo region and ergo region instabilities?
They don't have an ergo region, no. So the black hole doesn't have an ergo region. Yeah. So it's a very okay, I've swept the strangeness under the rug, right? I've focused on the interesting features here, but there's features such as the lack of ergo region that make them also a little strange in a sense, right?
Okay.
Yeah. Okay. So yeah. Just to be clear, like thanks for the question, right? I've emphasized the interesting properties of them that make them closer and closer to Kerr, but of course they aren't Kerr, and Kerr does not exist as a special limit or anything, or of these geometries. They're still very far away from realistic black holes, right? So they have no ergo region. They're still extremal, which means they have zero temperature, and so you don't really expect them to be realistic. But if realistic or not is a spectrum, right, with Kerr on one hand, on one side, and maybe supersymmetric black holes on the other side, then this is moving from supersymmetric towards Kerr in some sense. Okay.
Can I ask a quick question? You've got you said you can engineer M2 to be the same as Kerr. Are the odd multipoles the ones that are zero in Kerr? Are they large for these geometries, or are they just also very, very small?
Right. So it depends. It depends a little bit on the details of the geometry. Roughly speaking, they're always going to be This is sort of the way that you understand the size of these multipoles, right? So what is true for Kerr is true in general. If your black hole is highly spinning, then they can be very large, right? Because then A is large, and so these guys are quite large. And if it's not spinning much, then then all of the multipoles are also going to be comparatively small. Now, if you're asking, are they measurably huge? Then I think the answer is no. They'll be typically of the same order as the other multipoles.
May I also ask a question about this point?
Sure.
Are these, so for the black hole case, are these multiple moments spin induced like in the Kerr case, in the sense that if I fix the mass and the spin, is the entire multipolar structure fixed in terms of coupling constants, or there is more freedom as compared to Kerr?
Yeah, so there's more freedom, basically because, it depends a little bit on exactly what black hole you're talking about. So for example, for the almost BPS black hole that we constructed in this paper, we have a few parameters which roughly you could think of them as tuning the coupling between the scalars and the gauge fields, for example. So the entire theory that this lives in is gravity plus some scalars plus some gauge fields, and then so there's some couplings that couple the scalars and the gauge fields, and by tuning these parameters, you can tune, for example, Q over M, and you can also tune the M2, and so the structure of the multipoles depends a lot on all of these different things, right? In general, I think what you can say is that the multipolar structure depends on all of the details, right? It depends on the charges of the black hole. It also depends on all of the couplings between all of the fields in the Lagrangian. And so in general, this is going to be some very complicated structure.
Okay, thanks.
Okay, any further questions? I'll move on. All right, so I'll move on then. I'm going to skip multipole ratios just out of interest of time. I just want to very briefly touch on some tidal issues, right? This is also stuff that we expect to be interesting in spiral phase, right? When the black holes are spiraling around each other in some orbit. And I wanted to mention tidal love numbers because I also feel this is sort of the logical continuation of the subject of multipoles. Whereas when you're talking about multiples of an object, you're really just talking about one object, right? And you're sort of characterizing its bumpiness, right? The multipoles tell you more about the intricate structure of the bumpiness of the object. So this is where you're only looking at one object, whereas tidal love numbers tells you how this object deforms when something else is pulling and pushing on it, right? So if you have some object and you pull and push on it with tidal stresses from another object, then you might expect the object to deform, and so also the multipoles to deform. And so tidal love numbers, I'd like to think of them as a rate of change, a rate of deformation of these multipoles due to tidal stress of some other object. Okay, and so these, again, like I said, these have some effect on the gravitational wave. However, whereas multipoles are something that are relatively easy to calculate, right? So as I said, this is like a 1/r expansion, simplistically speaking. Tidal love numbers are much harder to calculate. And so what you need to do is you need to have some solution, some object, and then you perturb the object and then solve the equations of motion for the linear perturbations around this object, right? So this is in general a very hard thing to do because you need to perturb the full equations of motion. Now, what is known, just to give you an idea of things that have been calculated. For example, for let's say Einsteinian black holes, we're pretty sure now. Schwarzschild has been settled for a long time. Kerr, there was some recent debate, but I think roughly it's now being settled that the tidal love numbers of Schwarzschild and Kerr are 0, exactly vanishing. Other static black holes have also been studied. For example, Einstein-Maxwell, where the love numbers also vanish. But it's important to sort of point out that this is a very special result. This is very, very special for black holes. And so even if you look at static black holes, even in modified or higher derivative gravity, then typically the tidal love numbers will start not vanishing anymore. And for any kind of an object, you also expect the tidal love numbers to not vanish. So certain objects have been studied already, and you have explicit expressions for these tidal love numbers, and all of them are then non-vanishing. They might be small, but they're still non-vanishing. And so I think a very important question to ask is, what are the tidal love numbers for fuzzballs, right? For any fuzzballs. Because this is such a hard question, right? Remember, you need to perturb the full equations of motion. This is not something that has actually been studied before. But I think it's a very interesting question, right? To even just have some kind of an order of magnitude estimate as to what these things might be for fuzzballs. So this is, if you will, some open question that you might be interested in. The second kind of tidal-inspired issue that I'd like to briefly touch upon is geodesic deviation and tidal stresses from a stringy point of view. Okay, so there's various authors have looked at geodesic deviation in microstate geometries and found that the tidal stresses actually become much stronger become strong at much earlier timescales, or much further away from the microstructure than you might expect, right? So what you what you expect is, so this echo time scale, just to put it into perspective, the echo time scale is roughly the time that a light ray needs to travel all the way down, explore the microstructure, which I call the cap here, and then travel back out, right? So this is sort of, right, and then you get an echo from whatever wave that you've sent in. So this takes about, this is a time scale of the order of the length of the throat, which in this kind of a geometry in a superstrata is roughly b squared over a squared. So the echo time scale, the time scale that you throw something in and it comes back out, is it tells you something about the length of the throat. However, what they find is that the time scale for experiencing large tidal forces is much smaller than this echo time scale. And so in particular, you can sort of picture this as having large tidal forces somewhere where you're not even exploring the microstructure really yet, or at least you thought you weren't exploring it yet. I think this is a very interesting thing to point out, because this might have, you might think that this has some observable consequences, right? And in the following sense. So this is, again, this is an analysis done by Martin Mick and Warner. I think we're going to hear more about tidal forces on Tuesday, by the way, and also on the talks and panels on Friday. So I look forward to that. But so you can ask yourself, what happens when I throw in not a particle, but a string, right, into this kind of superstrata geometry? Well, when the string hits the tidal forces here somewhere, half the way down the throat, the tidal forces are going to want to stretch and pull the string, right? And because it's stretching it, it's going to start vibrating. And a string that effectively vibrates, well, what you've really done is you've taken the kinetic energy from the string falling in, and you've translated that or put that into some effective mass of the string. Right? And so if I'm allowed to sort of speculate on how you might take this chain of reasoning further, you might think that photons that are really close to the horizon, that are probing exactly this scale here where tidal forces become important, so that are not quite exploring the microstructure maybe, but are exploring the scale of the tidal forces. Maybe these photons or other objects will have these effective tidal forces stretching them into stringy objects, right? And so in particular, if you think about orbits of photons, things like photon rings, you might be able to see some deviations from your null geodesic photon expectations because of these stringy tidal force effects, right? And so that's sort of a very speculative idea that you might have on that. Okay, so that's all I said about tidal issues. I'd like to use the rest of my time to talk about shadows. I'll pause here again if there's any questions on tidal forces or multipoles. Please feel free to ask.
Comment that the photon ring is, of course, very much further out than where these tidal forces get large.
Yes, that's right.
It's going to be a tiny effect.
That's right. Yeah. So okay, so photon ring is probably not the right place to think of this. But yeah, like I said, this is a very speculative idea, but yeah, you're right to point out.
But that's because you're doing supersymmetric microstate geometries. I mean, in principle, if you have large tidal effects for let's say, 2 years from now will be the nice non-supersymmetric microstate geometry, the photon ring doesn't need to be far away from the structure. It can be.
Yeah, but the large tidal forces usually occur because you're seeing ultra relativistic velocities of infall.
Oh, I see. So you're saying that the photon ring.
Then magnifying the multipoles. So you have to get to a point where the probe is ultra relativistic.
I see, and the photon ring is not there by construction. Okay,
it's getting on the boundary of it. It's getting close. Yeah. I mean, it's the photon ring after all, but it's not enough to give you a huge amplification. Right. There might be a small deviation. I've got to change hats. We're coming up on almost the hour, but so you've got hour 15. You've had a lot of questions, so.
Yeah. I'm running a little behind schedule, but I'll try to stick roughly to the schedule. Yeah. Tell me if I'm running out of time. This is also my last topic, so this is where I'm talking about this specific paper. Okay, unless there's any other questions, in which case interrupt me now. I'm going to go on to talking about Fuzzball Shadows. Okay, so this is again, this is not talking about gravitational wave observations. This is more talking about the images that we might get at EHT or related experiments when we go out and we take a picture of the black hole, right? So this sort of what I'm going to talk about now. There's been some earlier work on, for example, geodesic trapping and works on various aspects of geodesics. But I'm going to be focusing on our paper that came out recently, which was really investigating this. I think for the first time, really having images of actual fuzzballs in 4D, right? So having an understanding of what these geometries look like when you consider nil geodesics in them. And so the two questions that I want to have in mind, or want you to sort of think of when I'm going through this, is one theoretical and one more observational, right? The more theoretic question is, okay, if we have a black hole, we know that it's black, right? The geodesics trap are fall in and they disappear. And so how does a fuzzball achieve this blackness, right? How will a microstate geometry or fuzzball mimic the black hole in this blackness factor, right? In particular for as in the image. And so that's the first question I'm going to address and answer. And then the second question is, can we, okay, so once we understand how fuzzballs are black, can we distinguish the black hole from a fuzzball at observations such as the EHT, right? Are there smoking guns that we can look at or generic features? How can we distinguish them? Okay, so now the setup that I'm going to be working with, it's not super important exactly what the geometry is, but just for people interested, let me introduce it very quickly. It's a 4-dimensional supersymmetric multi-centered geometry, although I say multi-centered in quotation marks because it's not really based on centers. So there's one center which is going to be a D6 brane with fluxes, and one center which is going to be an anti-D6 brane with fluxes, right? So if you use the Gibbons Hawking metric charge language, this is like a V is 1 and V is -1 center. And then on this ring here, so if this is the Z-axis, then this is sort of the XY plane. On this ring here, we're going to put a bunch of D0 branes. And what you should imagine is that you sort of smear all of these D0 branes into a uniform charge density ring. Okay, and so what I'd like to emphasize about this geometry is two things. One is this is a perfectly acceptable geometry I have not made any approximations. This is a perfectly acceptable geometry in this supersymmetric multi-centered in quotation marks ansatz. And it's a scaling geometry, which means that I can bring the centers as close to each other as I want. There's a tunable parameter lambda, which I will need in a minute. Which I can bring the centers as close to each other as I want, and so I approximate a black hole as well as I want. And I think it's the first or only known axisymmetric geometry of that kind, right? So there are other axisymmetric scaling geometries which are sort of fake scaling, but this is a true scaling geometry that is also axisymmetric. So I think that's kind of cute. Now, how are we going to image this? Well, we're going to imagine that we put this object at the center of a sphere. A very, very large sphere where we've colored in each quadrant of this sphere into 4 different colors. And then we put our camera on one corner of this sphere. And so we're looking at the object in the center of the sphere. If there was no object, of course, then what we would see is simply just a 4 quadrants, red, green, yellow, and blue in our image, but because of gravitational lensing, of course, we're going to see some kind of complicated color structure, which tells us something about the geometry. Okay, so let me actually show you the images that I'm talking about. So this first row here is the 4-color screen pictures that we get. Let me also say, I'm not sure if you can read this. It is in small letters there. This last column here is always going to be the black hole. And then these guys, these columns here are going to be microstates with lambda decreasing as we go to the right. So these are all, these four columns rather, are all microstate geometries. And then this last column is the black hole. Now, if you look at the 4-color screen for the black hole, it looks very reasonable. When you're far away from the black hole, you just see the flat space, right, which is sort of just the plain vanilla colors of the 4 quadrants. When you get closer to the black hole, you see that light sort of is able to travel around the black hole and come back out from the other side, which are these rings, right, this lensing ring structure. And then, of course, anything that actually happens to hit the horizon disappears and turns black. So that's very, very uninteresting in a sense, but also exactly what you expect. Now, when you look at the color screens for the microstate geometries, you see some very interesting effects. First of all, the first thing to notice is that when you're far away, you see exactly the same thing. So outside of the horizon structure, the same thing happens as for the black hole. You have the flat space limit and you have the rings around it, okay? This is the same. The difference is really with, let's say, the geodesics that would penetrated the horizon. These geodesics now explore the microstructure and they travel on chaotic orbits, right? So you can see that these orbits that they travel on are going to be very chaotic and very, very random. How do you see this? Well, it's basically because you see all of these, this crazy color structure in the center, right? That's telling you that, you know, nearby, because the nearby colors are so different, that's telling you that nearby geodesics are going to be traveling on very, very different orbits, right? So this is a signal of chaotic orbits. What you also see, of course, is that as lambda decreases, as you get closer to the scaling limit, as you approach the black hole limit more and more, this chaos becomes even more pronounced. Yeah, this chaos becomes even more pronounced. What's more is you see, and this is what you see in the second row especially, is that these chaotic orbits are very, very long-lived, right? So if you measure the coordinate time that it takes for the geodesic to escape the microstructure, that's what this color here in the second row is telling you. Of course, for a black hole, the time taken for the geodesic to escape the horizon is infinite, so it doesn't escape. But what you see in the microstructure is also that as you will, again, decrease lambda, increasingly many of the geodesics take an incredibly long time to escape these chaotic orbits around the microstructure, right? That's what this increasing yellowness is telling you. And in particular, a lot of the dots here that you see are black in this smallest microstate. A lot of the dots that you see here are black, and that actually indicates that we've cut off the integration, right? The numeric integration of the geodesic at some very, very large coordinate time. Right, it's not that it gets swallowed up by a horizon or anything, because there is no horizon. It's just that it's taken so long to escape the microstructure that we've sort of given up on it after a while, right? And that's just indicative of the fact that these chaotic orbits are very, very long-lived, right? So the geodesics get stuck on these orbits that are very, very long-lived. Now, what else is that these geodesics explore regions of very high redshift, which is this third row, and also high tidal stresses. Right? So again, the black hole, of course, anything that falls into the black hole experiences infinite redshift because the horizon is at infinite redshift, and infinite tidal forces because it falls all the way to the singularity and experiences infinite tidal forces. But what you see is that any geodesic that explores the horizon scale microstructure is also going to experience high redshifts and high tidal stresses. Okay, and this is really these are some key insights to take into account.
Can I ask a question about the
Yes.
last row? The color indicates at some point on its trajectory it experiences a large tidal force, because it's not. It's confusing on the black hole one because it looks like you're saying there's a high tidal force at the horizon scale.
No, right. It's just that any geodesic that enters the horizon, right? We're sort of hits the singularity.
So it's at some point on its path, it will experience a very large. Good.
Yes, that's right. Yeah. Right. So so this picture here is a picture of one single geodesic. This is just sort of also to illustrate this a little further. You see, well, again, this picture shows that it's a very chaotic orbit. The four panels here are all projections of the same orbit into a constant phi plane. This is again coloring according to the, sorry, this is not redshift, coloring according to the time taken, and coloring according to the redshift below. And so really all this does is just sort of reaffirm what we were saying before, which is that geodesics explore regions of high redshift, right? That's all this purple stuff that you see here. And it takes a long time to do so, right? Which is, if you stare at this long enough, you can convince yourself of that. But what I really want to emphasize is these 4 points together are what makes the fuzzball effectively black, right? So you have the geodesics that explore the horizon scale microstructure are follow chaotic orbits that are long-lived, right? We showed that, chaotic long-lived orbits that encounter high redshifts and high tidal forces, right? All of these together are important. Why? Well, roughly it's because, that's the next thing. Roughly it's because so this is sort of the picture that I have, right? This is a heuristic picture because what we've done is we looked at null geodesics, right? We haven't done this full back reactive solution or analysis, but this is what we would expect to happen. A light ray falls into the microstructure, gets bounced around a lot, experiences at some point a very, very high tidal force, right? And once you start experiencing large tidal forces like this, you're experiencing also for a long time, right? Because the orbit is long-lived. Then what you expect to happen is that this will not simply continue on being a nice null geodesic and mind its own business. What you really expect to happen is that this thing will interact with the fuzzball and create an excited fuzzball state, right? Where the geodesic has created some excitement at this point. Okay, so that's what that's what I feel the tidal forces are telling you, right? Is that the tidal force is going to want to pull this geodesic apart, pull this photon apart, and make it interact with the background. And then this excitation will, on average, want to emit new photons, which, of course, since they originate from a point of high redshift, that's where this high redshift comes important. If this photon is the one that we eventually see, this is going to be a highly redshifted photon, right? And so in the end, what you expect is not the photon that has originated from infinity on our color screen or whatever to travel around the microstructure and be the same photon that exits the microstructure. It's really some complicated process due to this interaction with the tidal forces and the redshift that gives you in the end some kind of highly redshifted photon back out that ends up hitting the camera, right? And that's sort of how we understand that the fuzzball will look effectively black. Okay, now let me just very briefly say this before moving on to the last slide of the fuzzball shadows. So what you can do is you can take this 4-color screen and you can darken, right? Because realistically, what we would want to do is we want to do the actual back reaction calculation to study what I was just talking about, right? This whole process of absorbing and re-emitting photons. But as a proxy, what we can do is we can darken the 4-color screen according to the redshift that I showed you before. So this is what we've done here. These 3 panels here, here, and here, these are all microstates, and this here is a picture of an actual black hole, a Kerr-Newman black hole. And so what you can do is you can sort of compare various aspects of these microstates to the black hole. In particular, you can compare the size of the shadow because there's some kind of there's, let's say, roughly a 10% error or uncertainty in the size, the actual size that the EHT measures on the shadow of a black hole. And you can also measure the brightness at the center of the image. And so roughly there's an upper bound on, that the brightness at the center here is 10% of the brightness of the rest of the image. And so you can say, well, which of these microstate geometries is ruled out, right? And so the size will rule out this guy because it's too small, but these guys are actually fine. The other 2 on the diagonal here are actually going to be fine with the size. And if you look at the brightness of the center of the image, then this guy is quite bright and is almost ruled out, although it's within this 10%. And this guy here, which is still a microstate geometry, is completely not ruled out, right? So you can see that you have microstate geometry here that looks very, very much like a black hole. Okay, so let me.
We're almost out of time, so.
Yeah.
So.
Okay, that's fine. This is my last research slide before I wrap up. I just wanted to mention, so I've said before all the way at the beginning, right, that the EHT has a lot of problems to distinguish subtle gravitational effects. There's a lot of uncertainty in the plasma physics, which makes it hard to extract actual gravitational physics and probe the geometry. And so one way to get around that, right, what you need are things that are not going to depend on the plasma physics, or not going to depend on how the plasma emits photons. And one idea is the idea of looking at the higher order photon rings. This was put forth in this science paper. a short while ago. Right, and so roughly, if you think of the photon ring as this idea, the exact photon ring is this idealized circle where photons go around in circles forever, right? It's a closed circular orbit. Then realistic photons will actually not travel exactly on the circular orbit, but will travel on approximately the circular orbit a few times around the black hole and then escape, right? And so the nth photon ring is comprised of the photons who have gone around the black hole n times before escaping, right? So they tell you something about the structure of the photon ring. Now, to actually see through the plasma, you might need a relatively high n. Let's not go into details. But what I want to say is, if you look at the structure of the photon rings, what you see is that this is the picture of the ring, right? The unblurred picture of the ring. What you see is that each successive photon ring, right, higher n photon ring, will be increasingly narrow in width. So the photons are emitted in an increasingly narrow range, but will be also increasingly intense. So this is what's given here, right? You've sort of plots width versus intensity, and you see that this big mound here, this big low mound is the first photon ring, and then this small mound on top is the second and then third. Okay, and the way that these peaks behave, right? The way that they are more intense, the way that they are less wide, this is all governed by the intricate details of the geometry. And so as these people explain, this is a way that you can probe the geometry by just looking at the intensities and making plots like this of the photon rings. You can probe the geometry in a roughly plasma independent way. And so we have a paper that's almost finished, that's coming up, where we use this method to say, look, if you're just looking at things like the EHT image and things like jet power, you're not going to be able to distinguish even Kerr versus Kerr-Newman, but you can distinguish them if you look at these intricate structure of the photon rings. Okay, and I think the next question to ask is, what about fuzzballs, right? If you replace a black hole by a fuzzball, at what stage will you be able to see some difference and some interesting features in these photon rings? I do want to mention though that this is not something that we'll be able to see at EHT. Not only do you need a higher resolution, but you also need something that's much larger than the Earth. You need an effective telescope size that's much larger than the Earth, and so you'll need to go to some space-based telescopes for that. Okay, so I'm certainly out of time. That's all I wanted to say about shadows. Let me skip this. This is basically just saying there's a lot more observables, and for example, see the talks on Friday when Ben Krups talks about tidal forces and scrambling times. I'll just leave these experimental sensitivities up here, which is also not super important to go over, and just repeat the main message of my talk, of my whole philosophy here, which is that fuzzball phenomenology is something where we have these objects that are given to us from quantum gravity, right? So top-down motivated objects where we can study their observable properties and make make predictions or possibly identify what could be a smoking gun detection of string theory microstructure at horizon scales. So this is a new field with a lot of things that are still out there, just waiting to be done and waiting to be studied. And I think it's very, very exciting. Okay, thanks.
Thank you very much. So, questions, guys?
May I ask one?
Oh, go ahead, Paolo.
Hi, Daniel. Thanks. It was a very nice talk. I have a question related with the time the geodesic takes to exit the geometry in the shadow case, one of the slides that you showed before. So if I understand from this plot, the time scale is, say, hundreds of units of the mass of the black hole, right?
Yep.
Which is parametrically longer than the dynamical scale of the, say, object itself,
yep,
but not super huge. Say,
right.
10 to 7, 10 to 9, say, for a mass black hole, this I think is 10 to 3 seconds, if I'm not wrong.
Mm-hmm.
So in these respects, I would expect that it's true that it takes much more than standard photons, but it still comes out of the geometry in relatively short time. Unless, of course, lambda is much smaller than the
right.
one here. Does this mean that neglecting, say, possible absorption of photons one should see some light coming out the interior of the geometry?
Okay, so there's a lot of interesting aspects there, right? So yes, I think for the guys that I'm showing you here, this is definitely true. And like you say, very important point to make is, of course, you can make lambda arbitrarily small, and so the time that the geodesics will then, on average, take to come out are going to be arbitrarily large, right? So if you want, you can make this time larger than the age of the universe, and then it'll never come out. Now, okay, if we take these relatively small lambda geometries seriously, then some light will come out. And then I think what you said is true, right? So we do expect something to come out. Now, one question that you might have is, well, do we expect, what kind of light do we want? What kind of light do we expect to come out? And I think our reasoning is really there to say or to show that we expect the light that you send in not to be the same as the one that comes out, and we expect instead some very highly redshifted light to come out, right? So even though something might come out on relatively short timescales, it'll still not be something that you'll really be able to detect. But I mean, a short answer is yes, you do expect something to come out.
If I can make a remark here, in fact, the important thing, I think, the message is the bottom slide, because what we now know is that tidal stresses for this photon as it goes through start hitting the string scale. And as a result, as Emil and I showed, that basically excites the stringy nature of the matter, which makes it massive. And so suddenly this thing that went in as a photon is no longer a photon, it's a massive particle because it's got string excitations. And so therefore it's trapped forever. And the second thing also is that as a result of that excitation, it will probably shed low mass photons. So the tidal forces really are trapping the matter.
Yes.
So if you assume it stays a null geodesic all the way, you will see a little bit of light come out. But I'm certain that's not what happens. What happens is the thing falls in, it's tidally excited, it becomes massive and maybe sheds a few photons of extremely high redshift, because it's.
Yeah, that's exactly what I want to say too. Yeah, thanks, Nick. That's because the thing that whatever falls in is going to be so affected by the tidal forces that thing is not going to be the thing that comes out, but maybe some highly redshifted photons will come out, right? And so all of these things together are conspiring to make this effective blackness, right? The photon that falls in is tidally affected, gets stretched and stringy or whatever. And then it emits photons from the place that it's trapped, as Nick says. But the place where it's trapped is also a place of high redshift, and therefore you're not going to really see anything because it's so highly redshifted.
If I might make one other remark too, that just the graph at the bottom. The interesting thing about the tidal infall is the tidal forces hit string scale, but because the particle is traveling so fast, usually, the actual impulse delivered by the tidal forces is it's finite and actually quite manageable. So it might be amusing to try this with a time-like geodesic, ultra-relativistic, of course, and then estimate the impulse delivered to that particle by the tidal force.
Mm-hmm.
And that's actually moderate size. It's not large, and you can actually estimate the level of stringy excitation. And then you might say, okay, after 7 encounters with high tidal forces, it's gone, but maybe not in the first encounter.
Yeah, no, that's a very good way maybe to estimate how much energy you expect to be lost.
What's the viscosity?
That would be a great idea. Yeah.
Anyway, sorry, I'm supposed to chair this, so I should shut up and invite other questions. Any other questions or comments? So just to say, make a follow up on the remark I was going to make, which is, the whole, one of the most, Daniel pointed out, the exciting thing about one of the supergravity calculations on quark-gluon plasmas was the viscosity calculation. There's probably some kind of effective viscosity calculation you can do with using the tidal force interactions. I'm not sure whether it'll be the same impact or order, but it's certainly something we can try and do. Anyway, any other questions, guys? We're running up at 1 o'clock.
Can I
please
jump in? Hello.
Yes.
So I have a question regarding the comparison you had between echo time and tidal time.
Sure.
And I'd like to understand what you mean. I mean, obviously, time should have a dimension. So I'm trying to understand in what units you are comparing these two with each other.
Well, okay. So I think the important thing here is that it's a parametrically smaller time, right? So depending on what I mean, I think roughly this should be like the time, the dimensionful scale, which I don't write here, is going to be R, which is the Y circle, right? If you, so this is actually going to be a compact direction here, and so this sets the dimension scale. But that, I mean, at least for me, that doesn't really tell me much, you know, because this is sort of a tunable parameter in a sense.
Yeah.
So for me, okay, and also this is, you know, this is a higher dimensional object, so I don't really know how to relate this to anything realistic. So for me, the important thing to realize is that, you know, the echo time scale that you have is whatever it is, and if you make the microstructure very, very small to the horizon, right? This is something that I'm sure Paolo will talk about in the afternoon as well. As the closer you make the structure to the horizon, the longer the echo structure is, and or the longer the echo time is.
Yep.
But even for that, you can have a parametrically smaller time scale, which is this tidal force scale. Sorry, I'm not sure if that answers your question or not.
But well, I understand. I guess I want to understand what that parameter is. That yeah, but I mean, I don't know if what example you have here can be applied to a 4-dimensional example where I have a better sense.
Not immediately. No. I'm not sure if so I think also in the multi-center geometries actually this was not done in 4 dimensions. This was done in a 5-dimensional perspective. Correct me if I'm wrong. You're all in the audience, and so it's not obvious to me how to make this how to relate this timescale to an actual observable timescale, right, in 4 dimensions. But, yeah.
I'd say the only honest answer you could give really there is that to make fuzzballs, these microstate geometries work, you have to have more dimensions, and so the scale of the time scale is set by the scale of those extra dimensions. So you ask your favorite phenomenologist, what's the maximum scale of extra dimensions is consistent with observation today? I think it's about 1 millimeter, if I remember rightly. And that's, so all you can do is bound it by the scale of the extra dimensions.
Good. So maybe an even better,
I think the question was different, actually. Sorry for interrupting. I think the question Ayesha was asking was different. The question is whether the black hole is asymptotically 4 dimensions or asymptotically 5-dimensional.
Right.
That was the question, because, you know, somehow if you have asymptotically 5-dimensional black holes, the physics is going to be different than asymptotically 4-dimensional black holes. And, you know, one of the issues we have is that, you know, superstrata, we can only build them asymptotically 5-dimensional, and we can solve the wave equation in them. So we can do stuff with them, but, you know, the price is to work in 5 dimensions. Bubbling geometries of the type Nick and I have been, you know, working on for, like, you know, the past 15 years, those guys, you can build them in 4 dimensions, asymptotically 4-dimensional. And, you know, in principle, those can give you nice 4-dimensional microstates. That's what we used with Daniel to compute multiple moments. And, you know, the guys in Roma did the same. But the problem is you cannot solve the wave equation in them because, you know, they depend on 2 variables. So there's a price to pay. If you want to go to 4 dimensions, you know, you lose separability, you lose the equations, you lose the ability to do nice calculations, at least for now.
But in the spirit of this conversation, I still the answer I think is still the same. Whatever time scale you've got, it's going to be set by the scale of your compactified dimensions. So I think that's still true.
Yeah. So if you will, from the point of view of just the 4-dimensional object, you can set the echo time scale at however you want, and then the dynamics of the object will tell you what the tidal time scale will be. Right, you set the echo time scale to be whatever you want by tuning the extra dimensional size to be whatever you want, and then the tidal time scale will be fixed, but will be parametrically smaller than that echo time scale.
Well, but I mean, at least for the echoes that I'm familiar with in 4 dimensions, and maybe this is a difference between finite temperature and 0 temperature. So the time scale is effectively the mass of the black hole times some log. And that log is regulated by the UVS scale, by the Planck scale, or whatever is your UVS scale, but it's only within the log. So if I change that UVS scale by orders of magnitude, the log doesn't change very much. So I guess I'm just trying to understand, is this is that the kind of echo time scale you're talking about, or is that or is the parametric changes inside the log or outside the log? I guess that's
Right. So okay, so the log that you're talking about is like if you have this, if the microstructure goes out to epsilon beyond the horizon, then it's log epsilon, right? Yeah.
That's right, exactly.
I think that's a good question. I don't really know how to. Okay, so there's reasons why this is a hard question to ask in supersymmetric geometries or extremal geometries in general, and that's because this epsilon that you're talking about is like how far, right, in sort of a proper distance way, is the microstructure from the horizon. But this question becomes meaningless in an extremal geometry because the black hole is at infinite distance. So it just becomes a hard question to even ask.
You can actually discuss, for example, there's a crossing time. So, for example, the infalling observer falls down in a finite time. So if you look from the perspective of an infalling observer, the microstructure is really, really close to the horizon. It's below the Planck length. I mean, the time it takes from the observer from the time it reaches the microstructure location, even from the time it reaches the high tidal location, which Nick will be talking about, even from there to the horizon, the proper time of the observer is going to be sub-Planckian. So
I think we should break at this point because we've got an hour for lunch. So let me just basically say we'll resume at 13:55. Joseph, do you want to stop